Okay, as I told you last time, this is problem 2 in the book on page 10. And it was 2x1 plus 4x2 equals minus 4. Now just make sure that I get this up here. Translate it to my book. Sometimes I start out on one problem and I end up hybrid problems. The rest of it's on another problem. Now, what I promised you I was going to do is, did we solve this one last time? Okay. And what I want to do with this is I'll let you, those of you that weren't in class and saw it, solve it just by the methods of simultaneous solutions. But what we'll do is we'll do a matrix solution for this problem. And I think the solution, I think I cut it from my notes. I think the solution was 7 and 12. X2 is minus 7. And x1 was 12. Now, what we want to do is I want to show you how the matrix works to solve this. And we're going to, in the next section, we'll study how to switch these matrices around to make the solution. But what you do is you make a matrix by the numerical coefficients of the x1 and x2. So this column is going to be x1 values, and this column is going to be x2 values. So the first equation, it's 2. For the second equation, it's 5. For the first equation, x2 numerical coefficient is 4 and 7. Now, this is, if I did this, that would be called the matrix of coefficients. But what we're going to do is we're going to do something called an augmented matrix. So what we're going to do is we will take the values that are on the right-hand side of the equal sign, put them in. And now this is the augmented matrix for the equation. Now what we want to do is we want to get this diagonal coming down here to have 1s in it. And a 0 here, a 0 there. And then our values over here are going to be our solutions. So several row and column operations. I can switch rows, can't switch columns. I can switch rows. I can do operations on rows. And you see where I'm going? Let's just, you'll see that it kind of leaps out at you what it is. Now, you see this row right here? I got a couple choices. The first thing I want to do is I want to get a 0 in this position. I could choose to multiply this number by 5/2 negative, and then bring it down here, and it would go to make that 0 by taking that whole row multiplied by 5/2 and bringing it down. This is what I'm going to choose to do. I can see that this row, I can divide 2 into it. That would be like taking this particular thing up here and taking 1/2 across. And I can do 1/2 on both sides, right? Same difference. So I'm going to take my matrices and I'm going to divide by 1/2, or not divide, but take 1/2 of it. So this is going to become a 1, this is going to become a 2, and this is going to be a -2. And then I have a 5, a 7, and an 11. You see that? No different than taking 1/2 of that, both sides. That first equation, right? Now then, what I'm going to do is I want to get a 0 right here. And that would be like trying to eliminate in this original problem this 5, this 5x in this equation, get rid of it. And so what I'm going to do is I'm going to take this row and multiply it by -5 and combine it. That would be just like multiplying this divided by 2, multiplied by -5, and then subtracting it from the equation, right? That's what I'm going to do. I'm going to multiply this row by 5, and then I'm going to combine it with this row. That will take, my first row will still look like this. Now then, my second row, multiplying first row by 5, combining it with the second row, this becomes 0. First row by -5, so this is 2 times -5 is 10. Combine it with 7 is a -3. -5 times a -2 is a +10. This is 21. This is where you got to watch me on this thing, because I tend to not be able to multiply, divide, add, or subtract. So these kinds of things, operations, I can get pretty confused. So with me? Can you understand why it's possible to do it? Now, I want to now get a 0 in this position. But the other thing I can do is I'm looking at this and I'm saying, I need a 1 eventually down here. And I'm going to get a 1 down there before I get a 0, because when I divide 3 into that thing, -3, I will get that 1. And to me, it's a higher priority to get the 1 than it is. And that would be just like taking that new equation and dividing it by a -3.
Third column. Over, it should be maybe a 2.
Oh, thank you. Yeah. Yeah. You have to be careful. Thanks. Okay. That would be pretty. It'd make the answer come up. Anyway. Now I'm going to divide by 3. So then this becomes 1, 2, -2. And then this will become 0. And I'm dividing by a -3, so this becomes 1. That's what I'm dividing by -3, because my desire is to get this diagonal to have 1s. Then this is going to be a -7, right? You just got to kind of look at your matrix and see how you want to massage it. Now then, I want to get this thing so that 0s are off the diagonal. And then what am I going to have to do? Multiply this row. And that's what you usually do. Now when you do with this upside, you start off on the right-hand side and work your way back. So I started left, worked my way right. Now you start left, right, and work your way left. So I'll take a -2 times this and add it to that. So -2 times 0, don't change this. -2 times this makes that one go away. So I have 1 and then a 0, right? And I take a -2 times this, which is a +14. Add it to this, that becomes a +12. And now my last row is 0, 1, -7. Remember, this row is x1s, this is x2's. So when I substitute in, this is saying x1 is equal to 12, and x2 is equal to -7. Here's my answer. So you go with it for the diagonal being ones, the zeros, and that's called the reduced echelon matrix. I've got echelon matrix here, reduced echelon. When I go to reduced echelon, I get the solution. Now, when you go 3 equations, 3 unknowns, and you do it this way with an augmented 8 matrix, it's a little quicker. When you go 4 and 5 equations, 5 unknowns, they're really cumbersome to do by hand. This is a little more organized to do it. Any questions on it? I wanted to do a real simple one so that you kind of get an idea of how it's, what you're actually doing. Okay, the problems, they're 5 and 6. They say consider each matrix in the exercise 5 and 6 as the augmented matrix of a linear system. State in words the next 2 elementary row operations that should be performed. So let's look at 6. If you had something like that, what would you probably want to do first? Want me to write it up? On page 10, problem 6. I guess I'll write the problem up here. And 1 minus 6, 4, 0, minus 1, 0, 2, minus 7, 0, 4, 0, 0, 1, 2, minus 0, 0, 3, 1, 6. Have I got all of these numbers up this side? Okay. Now, it's saying, what would be the next, what's the next 2 state in words, the next 2 elementary row operations that should be performed in the process of solving the system? Well, we'd like to get this diagonal to be 1s. We'd like to get everything below that diagonal to be 0s, right? And then eventually then everything above. How about getting rid of that 3? That might be the first one. Or you might want to go in here and make this a 1, or maybe not. But probably the first one you would do is you would try to get rid of that one. So that you'd have an echelon, what they call echelon form, where you have numbers down your diagonal, not necessarily 1s, but numbers down your diagonal and 0s below them. So we'll go ahead, as long as we're spending the time, we'll go ahead and work on this thing. I haven't worked this one out. Sorry. 1 minus 6, 4, 0, minus 1. Now sometimes you can, if you're really brave, you can take shortcuts and do a couple operations at once, so you don't have to rewrite all these matrices. But when I do it, and I do things like shortcuts in class, it usually proves disastrous. Now then, I've got this stuff. And I said my desire is to get rid of that 3. And in order to do that, I'm standing in your way most of the time. You can always choose to move. Okay. Use this. If I use any other row, but this row, I will affect this number, right? So I need to use this row. And I would do what? I want to get rid of that 3, so I would multiply this row by -3 and combine it. Correct? So -3 times this row, I would get a 0, 0, because this 3 times 0 would be 0, and so when I added it in here, it would not affect it. -3 times 1 makes this thing go away. -3 times 2 is a -6. Plus 1, so -5. And the -3, this is a -3, isn't it? That's a plus 9. And 6 is 15. Okay. Now, you see I got in my diagonal. And my diagonal I'm always looking at is back from that to get my solutions. I can see that zeros are all over here. What would be your next choice? Very good. That's what I'd do. Then I would get a 1 here, and I'd get a 3 here, and then I'd be ready to do what? Go back up and eliminate that thing for 0, right? Then I'd have zeros above that. So I'd be starting over here, working back to get zeros above it. That make sense? So that's what I would do. Now the temptation always is to try to think and do a couple things at the same time. Divide and then do this one so I don't have to rewrite the matrix. But I'm not going to fall into that trap because I can't think that many things. Oh, you did change sides. You can come up closer to the front. Right? I won't bite. I really don't, do I? I don't bite. I don't even smell bad. -6, 4. I don't smell that good. I have to tell you a story. I worked with a lady. She was a nurse, and I don't know why she do it, but she would come. She wore so much perfume, it made me sick. Just, you ever been around people that do that? Whew. Nice lady. But boy, really. I just warn you, I don't use any aftershave. And he says, yeah, I could tell, right? Okay, here's 0, 0, 1, 2, -3. And then we're going to divide by -5, right? 0, 0, 0. Now I got my 1 here, and I got a -3. Now you see, we want to get zeros above this diagonal. And so you want to start on the far right to do that. And then I got zeros here. The only one I got to handle is right there. And you see I want to start with this one to work on this one because it's not going to affect that one. So what am I going to do? -2 times this, combine it here, and get rid of that. One. Tedious, isn't it? Tell you, if you think it's tedious, write that equation out. and then try to solve. You'll do one or two of them problems and you just go, ah, my head is hurting very hard, man. And now this row is the one that we're going to work on, right? Because we said we were going to multiply -2 times this one and go up there. That makes this a 0. -2 times -3 is a +6. With a -3 is a +3. Zero, 0, 0, 1, -3. I want you to know that we've already found a couple things. We found x1, x2, x3, x4. x4 is actually -3. x3 is 3. So we're well on the way of getting a solution to this problem. Now we got a choice. We can go ahead and eliminate this -7, or we can divide by 2, but eventually we're going to have to divide that 2 out. But what I'm going to do is I'm going to eliminate that 7. Because if I eliminate the 7 first, then I won't have a fraction, right? Understand? If I divide it by 2, then this would be -7/2, then I have to multiply by 2/7. That crap. And how many all of you love to deal with fractions? No, what? No. So let's eliminate the 7. And then we'll divide by the 2. Then we got to go up and work on that top. Okay, so eliminate the 7. I wanted to eliminate the 7, didn't I? You say, what is this guy doing? So I'm going to multiply this row by +7 and add it up here. That makes this thing 0. This one 0. And then, this one isn't affected. But I got 7 times 3 is 21 plus 4, 25. And I got 0, 0, 1, 0, 3. And then I got 0, 0, 0, 1, minus 3. Now I want to get rid of my 4, and I'm going to have to use this row to do it, right? So I'm going to have to do what? Now you see, I could have done a little bit of a shortcut back here by doing what? Eliminating my 7 using this row, and at the same time eliminating my 4, right? It's hard for me to think ahead. So I'm going to use this, eliminate 4, and so I have to multiply this row by what? -4 to do that one. So I got 1 minus 6 I'm tempted, but I'm not going to do it. Notice I resist the temptation. So I got -4. This is going to leave. How come there's a, oh no. I'm multiplying by this one. That's 0 and a -1. Oh, not a -1 because I'm multiplying this one by 4, right? Minus 4, correct? Then I'm multiplying this one by minus 4 is 12, and this is negative 13. Is that good? We good on that row? Okay. 0, 2, 0, 0, 1, 5, and 0, 0, 1, 0, 3, 0, 0, 0, 1, 5. I could divide this thing by 2 to get a 1 there, but then I got a fraction, right? I can go ahead and eliminate that minus 6 by multiplying by 3, right? I don't have to deal with fractions. So I'm going to make this a 0 by multiplying this one by 3. So it's 1, 0, 0, 0, and then 3 times the 25 is 75, right? And then 75 minus 13 is 62. Is that, did I do that subtraction in my head right? Is that right? Now, I'm willing to do the next step and not have to rewrite this matrix, because now what I want is a 1 there, and I'm going to divide it out. I don't think I'll get confused, right? So now I'm going to divide 2 into that. Get 0, 0, 0, 25 over 2. The whole process, I've saved this one step. (25)(2), and then this is 0, 0, 1, 0, 3, 0, 0, 1, minus. And so what do we have for an answer? X1 equals 62, X2 equals 25 over 2, X3 equals 3, and X4 equals minus 3. My hands never left my wrists. More fun than it ought to be, isn't it? All right, the next set of problems there say the augmented matrix of the linear system has been reduced by row operations to the form shown. In each case, continue the appropriate row operations and describe the solution. I've just done this one. I think that you should be able to do those kinds of problems with this example. All right. What time are we done? Tell me this. What time are we done? At 10:45. Let's look at exercises 11 through 14, and it says solve the system. And I'm going to say we're going to solve the system using augmented matrix. X1 minus 3x2 equals 5. Now I want to tell you something. If you have a set of problems given you, and they got x1 minus x3, and then they put equals 5 here, and then the next one, the best thing to do is to write your equation out just like this is, so that you can, otherwise you screw your darn matrix up. You understand what I'm saying? You see how they got this? This is a minus x1 plus, oh no, touch the board twice, it makes 12, plus x2 plus 5x3. And that's equal to 2. Then x2 plus x3 equals 0. Now, do you understand what I just tried to tell you? Usually what you would do is you'd see this equation written with the equal 5 right over here. You'd see this equation written out. Then you'd see this one with x2 here and x3 and 0. My suggestion is, if you're trying to set it up in a matrix, line up all your x1s, x2s, and x3s and leave blanks for the other ones. Otherwise, you're apt to get a matrix in a follow-up. So the matrix we're going to make then is going to be 1 minus 3, and for this position we'll do what? A 0, and then we'll put, to augment it, we'll do a 5. Then we'll do a minus 1, 1, 5, and 2. And then a 0, 1, 1, and a 0. Okay, any questions? That's, we've later augmented matrix. But I'm just telling you from experience, if the thing is written out, be sure that it'll be beneficial for you to rewrite it, line all of those things up so that you can get this thing set up. Because if you don't get this one set up right, you'll be in trouble. Now, we start on the left-hand side when we're trying to get zeros down here. Notice that the diagonal has values in it, and it nicely has ones in it, right? So the first thing you want to do is get all zeros before you start on the leftmost column, and then all we're going to have to do is take this row and add it to this row, correct? So I'm going to have a 1, 3 times 3, 0, 5. Adding it is going to be 0 minus 2, right? And then 5, and then 7, and then 0, 1, 1, 0. Okay. Now then you're going to have to get this thing right here eliminated, and this thing right here eliminated. So what we want to do is we got a couple choices. We could divide by minus 2 and get 1 there, but then I got all them stinking fractions. So I'm just going to go ahead and multiply this by 1/2, come down. Then I got that fraction down there, but that'll be easy to deal with because I'll just multiply, right, and 0 on the other side disappear. Or do you want to do it a different way? Just tell me. You have a
Did we have to get rid of the -1 first, or could we have gotten rid of the 1 in the second column?
we couldn't gotten rid of this one. That, I'm assuming you're saying this one right here. Because see how if we tried to use this row to come down to do it, we'd affect this. And if we tried to use this row, we'd affect that. Okay? You got to start with the top left part and then work on zeros underneath it. And then once you got zeros underneath it, then you go to the next column and look how you get zeros. And you're going to have to start with the second row. Looks to me like there's no way to get away from having fractions, is it? No matter what we do, we're going to end up with fractions. So, you tell me, bite the bullet. What you going to do? Divide by negative 1/2, make the 1 there, or do you want to multiply this by 1/2 and combine it down here and get rid of it? Either way, we got. I'm going to multiply this one by 1/2 and come down. I don't know. I have this strange feeling, like I think when I'm thinking ahead, that maybe that would be better. So now I'm multiplying the second row by 1/2, combining with this. So that makes this one go away, right? 1/2 times a -2 is 1, minus 1. And then adding it to this is 0. Then I go 1/2 times 5 is 5/2. And 5/2 and 5 is going to be 5/2 and 1. This is going to be 2/2 plus 5/2 is 7/2, right? Right, everyone? And then I'm dividing this by 2, so this is 7/2 plus 0 is 7/2. Have I done it right? This is adding, subtracting, multiplying, and dividing my heads. We're in a real danger zone. I'm going to say if everybody is agreeing with me, we're right. Because I'm not going so fast that you can't follow. We're good. Now, probably what would be best is to get this into 1, right? Because I got to go back up, and remember, you start on the right-hand side and work your way back. Then I can eliminate that 5, and then I can get my first solution right there. You good? I try to look at your faces to see whether you understand. This guy here, I tell you what this guy's done right here. You see, he practices. He goes home and he looks in the mirror, and he practiced the most blank look he could have on his face, so the teacher can never know whether he understands or don't understand. Never ask him a question, right? Right? That's what you do.
Sometimes.
Yeah, I know.
Try to think how to do that.
Okay. All right, so I always accuse my students of that. 0, and we've decided not to divide that out yet, haven't we? We could actually let's stay with our original proposal. And we said we were going to divide by 2/7, right? So that's 1, 1. So we got our matrix in echelon form. That means we got the diagonals with something in it. And we got zeros below. Now we have to go over here on the right-hand side and work our way back to do reduced echelon form. So what are we going to do? Got to get rid of the 5, right? And we're going to multiply this row by -5 is 1 minus 3, 0, 5, 0. Notice this one is not going to be affected. Multiply this one by a negative 5 and come up. So we got 0. This by negative 5 and come up, we got a 2. And then our bottom row, we actually know that x3 is equal to 1, and we're going to find out that x2 is equal to negative 1, right? Because I think I'm going to make this a 1 by dividing by what? Negative 2. So I'm going to go 0, 1 minus 3, 0, 5. 0, 1, 0. That makes this a minus 1. 0, 1, 1. I have to be very careful about getting all excited about something and then forget to keep my wits about me and my signs right. Now what do you think? Multiply row 2 by 3 and add it up here, and we get the 0 right up there. So we need that 0, right? So that's not going to be affected. This is going to go away because we're multiplying this by 3, combining it. Nothing here. Multiply this by 3 makes it minus 3. 5 is 2. And now we got 0, 1, 0, minus 1, 0, 0, 1, 1. And x1 equals what? Notice I got it echelon, reduced echelon form right here. x1 equals x2 equals negative 1, and x3 equals 1. Voila.
Got it.
We got her. Now, when you get a solution like that, it's actually called a consistent set of equations. So, like 15 and 16, it says, are they consistent? And then do not completely solve the system. So they're just asking you to work it far enough so you can see that they're consistent. But this one is consistent because it has, see, this is a unique point where those three planes intersect. Two planes intersect in a line, right? So you need two of those planes put together intersect in a line. And then those two lines by intersecting. And this is the point that share all three share common. That's what we found. Isn't that exciting? Yeah. All right. That 19 through 22 says determine the values of H such that the matrix is the augmented matrix of the consistent linear system. I'll do 20. One, minus 2, 4, 6. Okay, so if we knew what H was, then what would be our first outlet procedure? Get rid of that negative 2, right? And so what we would do is multiply this row by 2 and combine it, correct? So let's do that. 1 H minus 3 would not change. But now we're multiplying 2 times this, combining it down here, that makes us 0. 2 times H, combining it down there makes this 4H plus 4, don't it? 2, what did I do? 2H. Correct? And then I multiply this by 2, that makes this one 0, right? Now, in echelon form, what do we know this would have to be? 1. So I could do 2H plus 4 would have to equal 1. 1, 0. I said 1 and suddenly 0 here. Correct? Then we can solve this. 2H equals minus 3, and H would have to equal a negative 3 halves. So H with 3 halves, then that would make this one 1, and 3 halves up here, we could substitute in, we could find out actually what that value. Now, what is it saying? What does H have to be, isn't it?
Mm-hmm.
So we don't care about the solution. We could work out what the solution would be. So we found out what H has to be. So what I'm going to do, I'm going to say that, I'm not going to do any more of those problems. And I want to talk a little bit about the next section. And we've actually done talked a little bit about that as we've gone along here. If you look in your book on page 13 and read the definition, it says a rectangular matrix is in echelon form or row echelon form if it has the following 3 properties. All non-zeros are above any rows of all zeros. So let's just look back here. Right here, we're in echelon form, right? We have gotten this equation. Even here, it's in echelon form, isn't it? Everything. This is not in echelon form, this one, but this one is. Because if you read, all non-zero rows are above any rows of all zeros. See? So here's a row, a column. Well, anyway. The non-zero rows above rows of 0. So everything it's in echelon form because it meets that criteria. All non-zero rows are above any rows of all zeros. And it says each leading entry of a row is in a column to the right of the leading entry in the row above. So this one, there's nothing there, but this one, the leading element in that row that's non-zero is to the right of that one. And then this one, it's to the right of that one. And then all entries in a column below a leading entry are zeros. So this is a leading entry in that row, the zeros below. This is the leading entry in that one, the zeros are below. And then this one has no rows below it. So that's in echelon form. So it's in echelon form at this point. From here on down, all of these matrices are in echelon form. Every one of them. Because you have zeros below the leading term in a column. My terminology is not right. This leading term in this row, the zeros are below it. The leading term in this row, the zeros are below it. And this leading term is to the right of the one above it. That's so that you get this diagonal with non-zero terms in the diagonal and then zeros in the column below. Now, if you look, it says reduced echelon form, and that's what we did when we got it down in this form. This is a reduced echelon form. The leading entry in each non-zero row is 1. So this is the leading entry in that row, leading entry in that row, leading entry in that row. It's an echelon form because this leading entry is to the right of this one in this row above, to the right of that one, and they're all ones. And then it says each leading one is the only non-zero entry in the column. So this column, this is the only one that has it. And this one, this is the only one. So you're going for, to solve your problem, you're going for the reduced echelon form. That's what the definition is saying. Now, if you notice in the example, you can have it in echelon form and not have all, ones down that diagonal. Now, theorem 1 there at the bottom says the uniqueness of the reduced echelon form. So this particular matrix is unique. There isn't another matrix that can happen with that matrix. No matter how you do it, no matter how you do the row and column operations and whatever you do, this one, that's the only thing you can get. So that guarantees you that it does not make any difference what operations you do and what order you do it. The only thing is what we're going to find out is you're going to have to go left to right to get rid of the zeros below and right to left to get rid of the zeros above. Does that make sense? Now they're going to talk about pivot positions, and the definition of a pivot position on page 14. It says a pivot position in a matrix A is a location in A that corresponds to a leading one in the reduced echelon form of A. A pivot column is a column of A. So being we didn't switch any columns or rows, so this reduced echelon form, this is a pivot for that row. This is the pivot for that row, and that's a pivot for that row. So what they're saying is that back up here in the initial matrix, this is the pivot point, this is the pivot point, and that's the pivot point. And this is pivot column, pivot column, pivot column for those rows. If we had taken one of these rows and moved them around, then and to get that reduced row echelon form, then the pivot points would be in the initial and in the final. So that's what we're. Now there's a row reduction algorithm, and if you follow through it, you'll see that I have followed it as I work this problem. On page 15, it says, number one step, begin with the leftmost non-row column. This is the pivot column. So the leftmost column. Now, what you've got to do, and then the second one says, select a non-zero entry in the pivot column as a pivot. If necessary, interchange the rows to move the entry. Now, in our particular position, this column had a non-zero in that position right there. If it didn't occur that way, if this were a zero, then we'd want to take one of these other rows and move it up. That's what they're telling you there. You've got to have a number in this position. Don't have to be one, can be anything, but you got to have one. Then what, if you're moving one of these other columns, just be judicious about what you move. You move the one that appears to give you the best chance to not have fractions and things like that. But you got to have it up here, and that's what that step 2 is telling you. Then it says use row replacement operations to create zeros in all positions below the pivot. So notice that what did we work on first? We worked on getting zeros below that pivot. Then it says, I think I read 3. Yeah. 4. Cover or ignore the row containing the pivot position. So once we got all zeros below, then we said we were working on the next one. So we covered this one. We're not going to use that row again, because if we try to use it to get zeros below this, we won't affect a change. We'll actually go backwards. So they say, cover this row up, don't look at it, and then look at all rows below. And then it says apply steps 1 through 3 in the matrix. Submatrix that remains, repeat the process until there are no more non-zero rows. So you cover this row once you got the zeros below, then you work as this is the pivot, and then get zeros below it. And you just keep that process, and if the matrix is 5 or 6, you just keep that process going across. And then you'd be covering 2 rows the next time, and then 3 rows, and then 4 rows. Because you asked why can't we, remember that you asked the question, and you see that that's essentially what they're saying. Is don't look at the ones above, it'll mess you up and going down. And then step 5, it says beginning with the rightmost pivot. And when we got down to the point where we had it in reduced form, here, then we start. This is echelon form, zeros are below. Then we want to get it reduced, so you start over here. Well, here's echelon form, right? And we had decided to multiply it to get that 1 first. Don't have to do it. And then you get zeros above this, and then zeros above this one. And then eventually, what you're going to do is get it in reduced echelon form. So, and then the book says, and it's important, that to get this process down now, learn how to do the process. You know, the only way you're going to do it is you're going to practice on lots of different things. It looks pretty simple, but it's not simple when you get into it. I mean, it is and it isn't. Okay. Now, sometimes what you're going to have is you're going to have, it's not going to come out to a nice solution, or you may not have. Remember the statement is if you've got a set of linear equations, you have to have what? The same number of unique, independent equations as what you have variables to get a solution. Right? If you got 3 unknowns, you have to have 3 independent, consistent equations. If you have 4, you've got to have 4. Now, if you don't have them, then one of the variables become what they call a free variable. It can take a lot of different values, and depending on what that variable is, it'll affect the solutions of the other ones. And that's when you're, and that's what they're talking about, solutions in that linear on page 18. And you don't have the equation necessary to get unique. And then what will happen is sometimes you'll not have independent equations. One equation might be just a multiple of another one. Well, then what you got is you got 2 planes laying right on top of each other. You understand? Or 2 lines laying on top. So now then it'll give you a certain thing. It'll give you a true statement, but it won't be unique because that plane is there that's the same. And another thing is that they might be parallel planes or parallel systems. And when it does that, it gives you no solution. So that's when they're independent, then they're not parallel, or they don't lay on top of each other. They're dependent, they are on top of each other. So you got to have independent equations, and then you got to have consistent equations. Consistent equations mean that they have the one says you have consistent says you have at least one solution, and the independent says you have, if they're independent, then you have at least one. If they're consistent, you have at most. And if you have both consistency and independence, then you have at least one, most one, you got one. The book will only talk about consistent equations, doesn't talk about dependence. You can have dependence too. And then you can have these free variables. They talk about consistency and inconsistency, page 19 in the parametric descriptions of solutions. And they're saying the system is consistent and has free variables. The solution has many parametric solutions. So that'd be the situation where you didn't have enough equations. The equations were all consistent that you had, but you didn't have enough. So then what you would have is you'd have to assign a value to one of them to get the solutions for the other ones. So you'd have a parametric. Everything would be expressed in terms of that free variable. And then inconsistent, you don't have any solutions. And they're going to talk about back substitution. And the existence of uniqueness of the equations. And theorem 2 there is saying a linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. So this column over here, which is this, it's the augmented matrix. As long as you don't have something down here, and you have zeros all across here and have a value here, then that would be that would make it inconsistent, because it says a linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. So we had this thing here had zeros all across, and something over here, then it would not be consistent. Okay, and it gives you an example. If a linear system is consistent, then the solution set contains either a unique solution, there are no free variables, or infinite many solutions when there are free variables. And that would be if you did not have enough equations for the number of variables you have, and then you would get a parametric solution. So what we're going to do next time is we'll look at some of these example problems here, and then try to apply the theory that's in that section. I didn't give you full value because I didn't